Okay, so as a little extra, and because someone hasn't prepared a lesson for today, we are doing logic gates, because why not? So we have three basic functions of and, not, and or. These are like the ones that everyone will know, and you'll need if you're doing computing or lots of other things as well.
Like the right there. Same.
Yeah, give it the sign.
Yeah, I'll get it.
Okay.
Fair enough.
Okay, so there are constants and variables. Boolean symbols only have one value. Only have
One value.
two values.
Useful.
The values are they can only be 0 or 1. Okay, so because it's Boolean, you only have two values which it can possibly be. So they are either 0 or 1 for the things.
So 1 add 1 is 1.
Yes.
Wow.
So we have logic 1, logic 0, which can be considered as false. That is when it's off, low, open switch, anything that you want to call it like that. Logic 1
The data and logic plus the child.
is true, on, high, yes, switch that's closed, you know, anything like that. Okay, so we have truth tables which represent all of this. And truth tables look like this. You have A, you have B, and you have, in this case, Y, which is just going to be the extra, or the final value. So A can be 0, and B can be 0, so these are just the combinations. You can have 0, 1, you can have 1, 0, you can have 1, 1.
This always has to be written that way as well. Well, for the kernel maps as well, and stuff like that, they have to be written in this order.
Yes.
Yeah, maybe you should show the camera that.
Yeah.
They always have to be written in this order when you're putting it into a kernel map or something. Otherwise, it doesn't.
Because that's how it works. So.
Yeah. Okay. So, for an AND gate, when they're both 0, then it's 0. When only one is 1, it's 0. And when they're both 1, they are 1. So, pretty much, NAND has multiple inputs. The output's true if all inputs are true.
It's like multiplication. If you multiply by 0, it's 0.
I'm assuming for or, if one is one, it will be one.
Yeah.
And not, it's, if you have one.
Only true when both inputs.
Okay, it's literally how you think it would be.
Yeah.
Oh,
It makes perfect sense.
And that's a simple, isn't this an engineering
True.
science, of course?
And the output's false
Most
when
likely, yeah.
every other combination,
Yeah.
as shown here. Symbol for this.
This used to be an advanced star physics as well. Like.
Yep.
This is the symbol for. This is like the thingy, AND gate, and you can write it as A dot B or without the dot. It really doesn't matter. So, AND gates work like switches. You have, so this is pretty much what it looks like. Probably have a power supply.
Imagine.
So this is pretty much what it takes in place of. Both switches are open, nothing happens. One switch is closed, one switch is open, nothing happens. The other switch closed, other switch open, nothing happens. When they're both closed, you get things happening. So that's basically an AND gate. Then we have an OR gate. And surprise, surprise, it changes a bit.
You don't have to blink that.
It's
spot.
either.
Yeah, shoot. So, an OR gate outputs 0 for nothing and it outputs true if all inputs are true or one input is true. So if either one of these are 1, then you will get 1. And in this case, they are both 1, and that still works. So it's only false when all inputs are false.
Okay.
So the gate looks like this. You have y equaling a or b. Yes, it's plus, but it's or in this case. So an OR gate works like switches in parallel. That's not used. We have switch here, switch here. If one switch is closed, then current will run. If the other switch is closed, current will run. If both are closed, then current will run. The only time current doesn't run is when they are both off. That is the essential of it. Then we have NOT gates, which are also known as inverters. And they only take one input. So their truth table looks slightly different. They only have two rows like this. They have 0 and 1. And it is also known as an inverter, and you have 0 going to 1, 1 going to 0. So if input is true, output is false. Output is false, input is true. Yeah. Pretty simple stuff. So its gate looks like this. And its formula is bar. So a bar is not a. Okay?
Sure.
Yeah. So that's nothing too hard. You can have multiple inputs.
This apply.
Wait, this is an OR gate.
There's no diagram for switching.
No, cause the circuit's very, very weird. So, we then get into slightly more complicated ones, being NOR and NAND. NOR is not OR. So you have A, B, and you OR them, A or B, and then you NOT. So you NOT the entire thing. So you've got 0, 0, 0, 1, 1, 0, 1, 1.
That makes sense.
A or B is 0 here. A or B is 1. That and that. And then, because it's NOR and it's knotted, then this value here is 0, so it gets inverted to 1, and the 3 ones all get inverted to 0. So it's a NOR gate outputs true if all inputs are false, and outputs false for every other combination. Yeah. Its gate, you've got your kind of basic case around this.
Basically, we went from this and we did everything circular. We did everything circular from this. We did circuit and we did that. We did all that.
Oh, okay.
This little bubble goes onto the end of the OR gate, this bubble kind of signifies not
Yeah.
when it's on the majority of
Otherwise,
cases.
these will
So
come
in this
together.
case we have the logic gate of
You-
NOR, and
after you finish all-
its formula is as shown.
At least, yeah.
There's yet another form of OR,
Which
is called
more formulas as well.
EOR, or XOR, or whatever you want to call it, which is slightly more complicated again, where you have the symbol being a kind of circle with a OR through it. You've got 0, 0, 0, equaling 0 in this case. And then you have being 1, where it is 1, and 1, 0 is also 1. However, 1, 1 in A and B, or together, is 0.
Yeah.
And so it is only going to output true when the inputs are different. So if there's a 1, 0, they are different, then it will output 1, but for being 1 and 1 or 0, 0, it will output 0. So its state has an extra line along there, and then you have the thing looking like A XOR B, which is equivalent to not A and B, or B, wait, A,
Which order?
you
It's
are
not
A.
which order you use it.
Yeah, but I want it in alphabetical order. So A, not A and B, or A and not B is what this is equivalent to.
Yep.
It gets a lot of a mouthful, and that's only that. So you can then not it, and you get 1, 0, 0, 1.
What's that called though? Next or
Yeah. It's a exclusive NOR, which is, as you said, an E NOR, X NOR, however you want to say it. And it outputs true only when outputs are the same. So, let me just kind of.
These could have been named better.
I mean, it makes sense. Like,
Yeah, they make a lot of sense.
it's pretty much
So-
very self-explanatory what it is.
I can understand, but like,
What would you rather put down?
Yeah. Well, what would you call it?
I don't know.
When it comes to Alexander, get away.
Okay, and its gate, if you hadn't guessed already, looks like the exclusive OR with the bubble.
Yeah.
And then, and this is equivalent to not A and not B, or A and B would be with just not, or, and.
Yeah.
Yeah, so false when inputs are different, true when inputs are the same for X. And that is the first.
What about NAND, bro?
Hmm?
What about NAND? There's no
Yes.
Nan red.
So for NAND,
Red.
I mean, I know what NAND is, but why isn't there a NAND in this thing?
and
Just or.
so you do A and B,
No.
you do A and B, which is like that. So you get
Bottom one is 1, 2.
no.
No.
Yes. It's wait. Not and. Never
Not
mind.
Yeah, it's not and.
Wait, then
It'd be
A
one,
and
one,
B.
one, one,
should be
zero.
put- Yeah, 1, 1, 1, 0.
Oh shoot, I can't write. I can't write. Yes, sorry.
You expect me to lean all the way back.
Yes, no, that NAND is like that, and NAND looks like. I have to get it right.
What about Nando?
Yeah, Nando's gate.
Yeah, Nando.
Okay, looks like that.
Sick.
Those are exclusive ands. Or exclusive nands.
We don't want that here.
You get a deal.
No. We then get onto part 2, which is more complicated again.
Oh no.
And this one here has NAND.
Oh, okay, it's nands.
Yeah.
So, NAND outputs false if all inputs are true. And it is true for every other combination. And as shown, that is what it looks like. Then we have NOR, which we have already covered.
Yes.
Did we?
Yes.
Yes.
Okay. Just go for it quickly again. Outputs true if all inputs are false. Outputs false for everything else. We have exclusive OR, which we have covered. We have equivalent gates. Oh shoot. So an equivalent to a NAND can be made by,
Two-thirds of this slide is like just the previous one.
Yeah.
More stuff.
this is what it can also be equal to. So NAND y is negative OR, not NOR, negative OR.
Yep.
And this is when you have the inverters before, so you have not A or not B. And then you also have negative AND, this is minus OR, and we also have minus AND. Which is equal to A, B, not A and not B. Now you have to be careful that these lines don't conjoin because then it becomes NAND,
Yeah.
and that's when you negativize the output, not the inputs. So this here is a NOR equivalent, and this is equivalent to NAND. And that is kind of the basics.
Yes, I think we're done. We can go get you.
What are you on about? Start Boolean algebra now.
No, not Boolean
No.
algebra.
So, with the basics out of the way,
Algebra.
oh, no Danny. Boolean algebra is performing symbolic logic. And symbols represent variables which can be either true or false. So, as before, algebra refers to the mathematical rules for combining symbols and manipulating symbolic expressions. You don't really need to know that, but that's basically what it is. When you combine binary and Boolean concepts, you have both symbols using only two symbols of 0, 1, true and false. Binary can represent logic, where 0 is false and 1 is true. Pretty basic. So we have some lovely laws. There are 11 laws in Boolean algebra, and they
We
give
will
us
link
some.
them in the description. We're not going over them.
We're not going over all 11, okay? So there's a law of
Just talking about just there's 11 laws. That's how many there is.
law of complementation,
Or and nor and.
where
Later,
A or not A
later they get a little bit
is equal to
more
1,
right now they're very much common sense.
where you have A, B,
A plus A bar is just 1 plus 0.
Yeah.
1.
yeah. So you have,
Easy.
so wait, that should be A bar. No, it is B. Oh, no. A or B. So you want when the values are different, you've got them different here. On the OR gate, you have 0, 1, 1, 1. It always equals 1. So A or not A is always equal to 1.
Yeah.
And then you have A and not A, which is always equal to 0. So if we have A, B, A and B, 0, 0, 0, 1, 1, 0, 1, 1. We have 0, 0, 0, 1.
Yeah. It's an if. Yeah.
For both of these values, they are equal to 0, therefore A and not A is always equal to 0.
Yeah.
So we have intersection, slightly more complicated.
But not
This is-
circle.
So that was laws of completion. Now we have laws of union and intersection. Which we have I should probably write it out first. A and 0 is equal to A. And
Yes.
A or 1 is equal to 1. So, again, you've got the gates, you have 0, 1, 1, 1. If you add 0 to A, so A plus 0 is 0, and 1 plus 0 is 1. So, these two rows here, they both equal what A is, because they're adding 0. And then if you have A being 0 and adding 1,
You're right.
you get 1, or ORing is 1.
You're
And
right.
then if you have A being 1, B 1, or
Why
adding
do you
or
replace
1.
AB, why not A1?
Ah.
And write it up like that, it's a bit slightly short to write that.
Well, like,
Oh,
A1, A plus 1. Yeah,
like that.
yeah,
Yeah,
would
okay.
that be easier?
Yeah, probably. Okay, so that's that. And then you also have this for ANDing, where you have A and 0 is equal to 0, A and 1 is equal to A. So A and 0, as we know, AND can only be true when both inputs are true. Therefore, if you're ANDing with 0, you're going to get 0. When you have 1, however, there is the chance of it being 0 or 1, where we have A1, A and 1. This can either be 0 or 1. This here is 1 always. As we're ANDing, that's going to be 0, that's going to be 1. So it is then equal to each other.
You just missed Alexander trying to hit by his own shoe.
He does that all the time. It's
So
okay.
keep trying.
Okay.
Well, he did.
So now we have when we add them together and when we OR them together and AND them together. So we have A or A is equal to A, and the same is true for A and A.
Okay, why do you know these laws? Isn't that just part of the?
Oh, because you get questions on these.
Like they get longer.
Like you get A
Of course, you need to get
XOR
some
B
simple stuff,
XOR
yeah,
C,
natural things.
and you have to equate that to something. You have to like break that out into just and, or, and not.
And then preferably.
So you have to get rid of. Yeah.
Well, you simplify it to the simplest form.
Yeah, you simplify that to the simplest form.
So you can then make it into circuits.
Yes.
Sounds like fun.
This is electrical engineering.
Yeah.
So-
exactly.
0, 0, 1, 1. You have A.
Yeah, I'm probably doing mechanical anyways.
No, Dan, you're getting forced to do heroes so we don't have green mechanics.
I'll do error.
As you can see, is equal to A. Then we have 0, 0, 1, 1.
I'll use my knowledge of physics.
A and
Mechanical,
A
mechanical zero.
equal to 0 here, equal to 1 there. Quite simple. Then we get onto some slightly more.
What is this?
You've got your standard.
It's multiplying up brackets.
Yeah.
Yeah, you have
It's just.
A and B or C, which, as per standard maths, is equal to A and B or A and C. It's just like doing it with X and Y.
No way.
Wow.
Sugoi!
Okay,
There's a lot of laws after all.
Yeah.
you have
Oh,
both
it's awesome. No,
A
you're not
and
on
B
the so no,
or A and B naught is equal to A. So if A is equal to 1, B is also equal to 1, B naught is equal to 0. AB is equal to 1 because they're both true. A not B is equal to 0. Therefore, if we have AB, A not B,
What did Mark say to them here?
A B or
What?
A
Boolean
B
algebra.
not, A not A and not B. Then you have 1, 0, it's an OR, so it's equal to 1.
Okay.
So 1 or 0 is 1, which is equal to A. The same will be true if we have 0 for A, and that sort of thing. So
Yeah,
that's
now we are
that's
done.
that's the most basic of basics.
Yes. And that is all we're doing.
That is all we're doing for now.
Wait,
Be sure to like and subscribe.